Hello everyone, and welcome to the training presentation from Links, where we'll be diving into GNSS vulnerabilities and PNT backup solutions, focusing on AI-based GNSS spoofing and jamming detection and classification tools developed in Task 2.3 of the ATLANTIS project. The mission of ATLANTIS, which involves 39 European partners with complementary roles and skills, is to enhance resilience and cyber-physical human security of the key European critical infrastructures, going beyond the scope of distinct assets, systems, and single sea ice, by addressing resilience at the systemic level against major natural hazards and complex attacks that could potentially disrupt vital functions of the society. The term Global Navigation Satellite System refers to a set of satellite constellations that transmit signals to Earth, which are received by specific receivers below the noise level. GNSS signals are used to determine the receiver's position, thus enabling navigation services, but also to obtain a very precise time information, allowing them to be used as time reference systems as well. These services take the name of PNT services and are nowadays used worldwide. In the context of critical infrastructures monitoring, targeted in ATLANTIS project, PNT services are essential to provide high accuracy and reliable positioning and timing information in different application domains, such as financial transaction systems, communication and electric grid networks. Nevertheless, the availability of low-cost software-defined radio hardware has simplified the possibilities to attack GNSS with the intention to disrupt the services, raising the awareness and making the GNSS more robust to interference attacks as well as in finding backup solutions. In the framework of the ATLANTIS project, the challenges posed by evolving threats to satellite navigation and timing systems are addressed through the development of AI-driven algorithms to support the detection and, wherever possible, the classification of a threat, and the adoption of potential 5G backup solutions. In particular, the presentation will explore more in details the taxonomy of possible GNSS vulnerabilities, focusing on attacks based on jamming, spoofing and meaconing techniques, and will describe AI-based solution developed in the framework of ATLANTIS project to detect attacks to GNSS signals. GNSS interferences can be divided into two main families: intentional and unintentional interferences. Unintentional interferences are non-malicious disruptions caused by sources that were not intended to interfere with GNSS signals but do so incidentally, like multipath, atmospheric and segment errors. Intentional interferences are actions taken deliberately to disrupt the normal functioning of GNSS systems through the emission of radio signals, like jamming and spoofing attacks. Even though non-intentional attacks could be considered a potential threat in critical applications and for such a reason to not be discarded as possible source of denial of services or reduction in performance and accuracy in PNT services, intentional attacks are the most dangerous ones, and will be the main focus in this presentation. Jamming in the context of global navigation satellite systems refers to the deliberate transmission of radio signals that interfere with the normal operation of GNSS receivers. This interference can degrade or even block the reception of GNSS signals by overwhelming them with noise or other unwanted signals. The impact of jamming on GNSS includes reduced accuracy, increased errors, or complete loss of the ability to determine position, navigation, or timing. Different types of jamming techniques include simplistic, broadband, and narrowband. Spoofing in the context of global navigation satellite systems is the intentional broadcasting of false GNSS signals that mimic the real signals emitted by satellites. This misleading practice is designed to deceive receivers into accepting the spoofed signals as legitimate, causing them to compute incorrect positions, navigation, or timing data. Spoofing poses a serious risk to systems that rely on GNSS for accurate and reliable positioning and timing information, such as those in aviation, maritime navigation, and financial transactions. Meaconing is a type of electronic attack where GNSS signals are intercepted, delayed, and then retransmitted. The purpose of meaconing is to mislead GNSS receivers by providing them with incorrect timing or positional information. This delay in the signal causes the receiver to calculate an inaccurate position. Meaconing differs from spoofing because it does not alter the content of the GNSS signals. Instead, it simply rebroadcasts them with a time delay. The effects of GNSS attacks, particularly through jamming and spoofing, can be significant and diverse, impacting various sectors that rely on precise positioning and timing. In the realms of aviation and maritime, the accuracy of GNSS data is critical. Pilots and ship captains depend on precise location information for safe navigation. If a GNSS attack occurs, such as spoofing, it can mislead a pilot or captain about their actual position, leading them potentially into hazardous areas or incorrect routes. For telecommunications, the synchronization of signals across cell towers is essential for maintaining the integrity and efficiency of data transfer. GNSS signals provide the timestamp needed for this synchronization. An attack that disrupts these signals can cause significant communication delays and outages, impacting everything from simple voice calls to complex data services that many businesses and critical services rely on. In the financial sector, milliseconds can mean millions of dollars in gains or losses. Financial institutions use GNSS-provided timestamps to synchronize transactions across global financial markets. A spoofing attack could alter timestamp data, leading to trades being executed at inopportune times, potentially causing financial losses or even undermining the integrity of financial markets. The implementation of AI-based GNSS jamming and spoofing detection technology holds significant potential for enhancing security, safety, and optimizing various business processes. By accurately identifying interference, these systems can substantially improve the reliability and trustworthiness of GNSS-dependent applications, especially within the critical infrastructures. The ATLANTIS approach to the detection and classification of GNSS jamming interferences is to perform time-frequency analysis, allowing to see the evolving variation of the power spectrum over time. Leveraging the short-time Fourier transform operator, a bidimensional representation of the frequency components with respect to time can be obtained. Consequently, the interference classification task is transformed into an image classification problem, where a model is trained to recognize the target classes of pixels or vectors within an image, and similar approaches applied to image recognition using machine learning techniques can be adopted. Deep learning algorithms, particularly CNNs, are especially effective for image classification because they efficiently capture spatial hierarchies in images through layers of filters. This allows them to recognize patterns more effectively than other algorithms, which is crucial for tasks involving visual recognition. The proposed solution is composed of different stages: a pre-processing stage, where the time-frequency analysis is performed, and a set of images of the spectrogram are created. An AI stage, based on a convolutional neural network classifier, where the AI model recognizes the target classes of pixels or vectors within the spectrograms obtained. The proposed technique can find real-world application in several use cases. Regarding the positioning navigation aspects, for example, a coordinated cyber attack on the French-Italian border could be a major issue, being the Frejus Tunnel a main transalpine roadway. In the event of accidents or emergencies within the tunnel, GNSS technologies play a crucial role in coordinating emergency response efforts. Jamming or spoofing attacks could disrupt communication and navigation, hindering timely response and rescue operations. Detection systems can ensure that emergency services maintain access to accurate positioning and timing information, facilitating efficient response. Regarding the timing synchronization aspects, for example, a coordinated cyber attack on the financial hub in Caixa Bank premises could lead the system to fail to provide accurate timestamps, leading to a breakdown in the synchronization of trades. Implementing GNSS jamming and spoofing detection as part of a comprehensive cybersecurity strategy enhances the resilience of banking operations, safeguarding the timing integrity and ensuring that transactions are accurately timestamped and processed in the correct sequence.